Imagine you have a panel with 8 light switches. Every switch is either on or off. That's it. And every single number your computer handles. Every age, every score, every pixel color is secretly stored as a row of these switches. The number 5 looks like this. Off off. Off off. On, 2 switches. The number 7, 3 on. The number 4, just 1 on. Now imagine someone hands you every number from 0 to n and says, count how many on switches each one has and give me a list. Simple enough. But here's the challenge. Can you build that list without manually checking every switch for every number? Because there's a pattern hiding in plain sight. A shortcut so clean that the entire solution fits in 3 lines. Binary is just powers of 2. Each position is a power. 1, 2, 4, 8. When a switch at that position is on, you add that power to the total. 0 is all switches off. 1 has just the unit switch on. 2 has just the 2 switch on. 3 has both. 2 plus 1. 4 has just the 4 switch. The count of on switches, the count of ones, is called the number of set bits. LeetCode wants that count for every number from 0 to n. Before I show you the fast solution, if this is your first time here, hit subscribe so you never miss a new problem. You have 5 seconds to try it yourself. Go. The obvious approach. Loop from 0 to n. For each number, scan all 32-bit positions one by one, check if each bit is on, count the ones, append to your result. This works. But you're doing up to 32 checks per number. A whole of n times log n total. For n equals 1,000, that's 32,000 operations. And worse, you're starting from scratch every single time, even though you already computed the answer for smaller numbers. There's a better way. Write out numbers 0 through 7 in binary. 0 ones. 1, 1, 2, 3, 2, 4, 1, 5, 2, 6, 2, 7. 3, look at the arrows. 2 in binary is 1, 0. It's just 1 shifted left. Same count as 1. 4 is just 2 shifted left. Same count as 2. 3 is 1, 1. Same as 1, with 1 extra bit at the end. 5 is 1, 0, 1. Same as 2, with 1 extra bit. Here's the rule. Take any number I, right shift it by 1, that's integer division by 2, and you get a smaller number whose answer you already have. Then check whether the last bit of I is a 1 or 0, I, and 1. Odd numbers have a last bit of 1. Even numbers have a last bit of 0. dpi equals dp of I right shift 1 plus I and 1. The bit count of every number builds directly on a number you already solved. Here's the full solution in Python. 4 lines. Create a dp array of size n plus 1, all zeros. For every I from 0 to n, dpi equals dp of I right shifted by 1 plus I and 1. Return dp. Let's trace for n equals 4. dp 0 is 0. I equals 1, dp 0 plus 1, that's 1. I equals 2, dp plus 0. 2 is even, last bit is off, still 1. I equals 3, dp plus 1, 3 is odd. I equals 4, dp2 plus 0, 4 is even 1. Result, 0, 1, 1, 2, 1. Matches exactly. The right shift divides by 2 and drops the last bit. The and with 1 reads just that last bit back. Together they let every number piggyback on a smaller number's already computed answer. Time complexity is O of n. 1 pass, constant work per step. Space is O of n for the dp array. Compare that to brute force at O of n log n, checking 32 bits per number. The dp version is strictly faster and strictly simpler. And unlike some dp solutions that feel like magic, this one has a clear reason. Binary is just doubling and halving. Right shifting preserves all the bits except the last. So the count carries over plus at most 1. Counting bits, solved in 1 line of dp. The insight, every number in binary is its parent right shifted, with 1 possible extra bit at the end. Spot the halving structure, and the solution writes itself. Drop a comment like the next problem you want me to break down. See you in the next one.